If you're watching on a smaller screen, consider switching to full screen for the complete experience. And if you'd like to follow more explorations like this, a subscription helps us continue. In the autumn of 2022, the James Webb Space Telescope transmitted to Earth a series of images that would quietly redefine the boundaries of observed cosmic structure. Within those images, processed through instruments designed to capture infrared light from the most remote sources ever detected, astronomers identified galaxies arranged not as isolated points scattered across an empty void, but as threads and filaments composing a vast, interconnected web stretching across regions of spacetime previously assumed to contain only darkness and the faint afterglow of the Big Bang. These galaxies were not merely distant. They occupied epochs so early in cosmic history that their light had traveled for more than 13 billion years to reach the telescope's mirrors. Yet they were not solitary. They were structured, organized, woven into patterns that suggested formation mechanisms and gravitational processes operating at scales and timescales that challenge the explanatory capacity of existing cosmological models. The term hidden web emerged not as metaphor but as descriptive necessity. A web because the distribution resembled a network of interconnected nodes and bridges. Hidden because these structures had existed beyond the resolving power of every previous instrument. Invisible not due to absence, but due to limitation. The discovery did not announce itself with fanfare. It surfaced gradually, embedded within datasets returned from Webb's near-infrared camera and mid-infrared instrument, both of which operate in wavelengths far beyond the visible spectrum. These instruments were designed explicitly to detect light that has been stretched by the expansion of the universe into the infrared regime, a consequence of cosmological redshift. When light originates from an object moving away from an observer due to the expansion of space itself, its wavelength lengthens. The greater the distance, the greater the redshift, and the further into the infrared the light is pushed. Webb's sensitivity to these wavelengths allows it to observe objects so distant that their light left them when the universe was only a few 100 million years old, a period known as the cosmic dawn, when the first stars and galaxies ignited within the cooling hydrogen gas that filled space. But the web of galaxies identified by Webb extended even beyond this already extreme frontier. Some of the galaxies detected were found at redshifts exceeding values previously considered the practical edge of the observable universe, meaning they occupied a region of spacetime that had remained effectively unobserved until Webb's deployment. What made these galaxies particularly significant was not simply their distance, but their arrangement. Earlier deep-field observations, including those conducted by the Hubble Space Telescope, had revealed galaxies at high redshifts, but they appeared largely as individual objects, scattered across the field of view without obvious large-scale coherence. The assumption, grounded in cosmological theory, was that at such early times, within the first few 100 million years after the Big Bang, the universe had not yet had sufficient time for gravity to organize matter into the vast filamentary structures observed in the local universe today. The cosmic web, as it is known in contemporary cosmology, is a feature of the mature universe, built over billions of years as dark matter halos attracted baryonic matter, forming nodes where galaxies cluster and bridges where matter streams along gravitational gradients. The presence of such structure at redshifts corresponding to the universe's infancy implies either that structure formation occurred far more rapidly than models predict, or that the mechanisms driving structure formation were fundamentally different in the early universe, or that what is being observed is not structure in the conventional sense, but a projection effect or selection bias inherent to the detection method. To understand the significance of this discovery, it is necessary to examine the physical process that govern galaxy formation and the observational techniques that allow those processes to be studied across cosmic time. A galaxy is not a static object. It is a gravitationally bound system composed primarily of dark matter, stars, gas, and dust, assembled over time through the collapse of primordial density fluctuations and the subsequent accretion of matter. These density fluctuations originated in the quantum perturbations present in the earliest moments of the universe, amplified by cosmic inflation, and imprinted as variations in the density of matter and radiation. As the universe expanded and cooled, regions of slightly higher density exerted stronger gravitational pull on surrounding matter, growing over time into the seeds of structure. Dark matter, which interacts only gravitationally and not electromagnetically, collapsed first, forming halos within which baryonic matter, ordinary matter composed of protons, neutrons, and electrons, could accumulate. When sufficient baryonic matter collected within these halos, it cooled and condensed, eventually forming stars. The light from these stars is what astronomers detect when they observe distant galaxies. The timeline of this process is central to interpreting Webb's observations. The Big Bang occurred approximately 13.8 billion years ago. For the first few 100,000 years, the universe was too hot and dense for neutral atoms to exist. Photons were constantly scattered by free electrons, rendering the universe opaque. This era ended with recombination, when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen, allowing photons to travel freely. The light from this moment is observed today as the cosmic microwave background, a nearly uniform glow at microwave wavelengths that fills the sky. After recombination, the universe entered a period known as the Cosmic Dark Ages, a phase lasting several hundred million years during which no stars had yet formed, and the universe was filled only with neutral hydrogen gas and the invisible scaffolding of dark matter. The first stars and galaxies formed at the end of this period, initiating the epoch of reionization, during which their ultraviolet radiation ionized the surrounding hydrogen, transforming the universe from neutral to ionized once again. This transition is thought to have occurred between about 100 million and 1 billion years after the Big Bang, though the precise timeline remains uncertain. Webb's discovery of a structured web of galaxies at redshifts corresponding to this epoch, and possibly earlier, suggests that galaxy formation was not a slow, isolated process, but a coordinated phenomenon driven by the underlying distribution of dark matter. The cosmic web is the large-scale structure formed by this distribution. Dark matter does not collapse uniformly. Instead, it forms a network of filaments, sheets, and nodes, with the highest concentrations of matter at the intersections of filaments. Baryonic matter falls into these dark matter halos, and galaxies form preferentially at the nodes and along the filaments. In the local universe, this web is observable through the distribution of galaxies themselves, as well as through the distribution of intergalactic gas, which can be mapped using absorption lines in the spectra of distant quasars. But observing the web at high redshifts is extraordinarily difficult. The galaxies are faint, both because they are distant and because they are often small and young, with fewer stars than mature galaxies. The intergalactic gas, though abundant, emits little light and is best detected through its absorption of light from background sources, which requires bright sources at even greater distances, a challenge when observing near the edge of the observable universe. Webb's ability to detect this hidden web relies on several factors. First, its large primary mirror, measuring 6.5 meters in diameter, collects far more light than smaller telescopes, allowing it to detect fainter objects. Second, its instruments are optimized for infrared wavelengths, where the light from high redshift galaxies is strongest due to cosmological redshift. Third, its position at the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth, places it far from the infrared glow of Earth's atmosphere and the thermal radiation of the Sun, both of which would otherwise overwhelm the faint signals from distant galaxies. Fourth, its sensitivity and resolution allow it to distinguish individual galaxies even when they are closely spaced on the sky, which is essential for mapping the structure of the web. Finally, its instruments can perform spectroscopy, splitting light into its component wavelengths to measure precise redshifts and determine the physical properties of galaxies, such as their star formation rates, chemical compositions, and ages. The process of detecting high redshift galaxies begins with imaging. Webb's near-infrared camera captures images in multiple infrared bands, each corresponding to a specific range of wavelengths. When light from a galaxy is redshifted, its spectral features, such as the Lyman break, a sharp drop in flux at wavelengths shorter than 121.6 nanometers in the rest frame, caused by absorption by neutral hydrogen, are shifted into longer wavelengths. By comparing the brightness of a galaxy across different infrared bands, astronomers can estimate its redshift through a technique called photometric redshift determination. This technique relies on matching the observed colors of the galaxy to models of galaxy spectra at various redshifts. Once candidate high redshift galaxies are identified, follow-up spectroscopy can be performed to measure precise redshifts and confirm the photometric estimates. Spectroscopy involves dispersing the light from a galaxy into a spectrum, revealing emission and absorption lines corresponding to specific elements and physical processes. The wavelengths of these lines, compared to their known rest frame wavelengths, yield an exact redshift measurement. When astronomers applied these techniques to Webb's early deep field observations, they found galaxies at redshifts previously unattainable. Some galaxies were detected at redshifts exceeding 13, corresponding to times less than 300 million years after the Big Bang. This alone was noteworthy, as it pushed the frontier of observed galaxy formation back toward the earliest possible epochs. But more striking was the spatial distribution of these galaxies. Rather than appearing randomly scattered, they tended to cluster along lines and curves, forming elongated structures that extended across the field of view. When multiple fields were observed and the positions of galaxies were plotted in three-dimensional space, using their redshifts as a proxy for distance, the pattern became clearer. The galaxies were not isolated. They were nodes in a network, connected by what appeared to be filaments of enhanced galaxy density. This was the hidden web. The term behind the known universe requires careful interpretation. It does not imply that these galaxies exist in a separate realm or dimension, nor that they are located beyond the physical extent of the universe. Instead, it refers to their position in observational space. The known universe is defined by the observable universe, the region from which light has had time to reach us since the Big Bang. The edge of the observable universe is not a physical boundary, but a horizon determined by the finite speed of light and the finite age of the universe. Light from objects beyond this horizon has not yet reached us and never will, because the expansion of space is carrying them away faster than light can travel through space. The observable universe is thus a sphere centered on the observer, with a radius of approximately 46.5 billion light-years, larger than the age of the universe in light-years due to the expansion of space itself. The galaxies detected by Webb are not beyond this horizon. They are within the observable universe, but they occupy regions of space-time that were previously unobserved, hidden not by distance alone, but by the limitations of prior instruments. In this sense, they were behind the known universe in observational terms, concealed within the gaps between the most distant galaxies previously catalogued. The discovery raises immediate questions about the physical mechanisms responsible for the formation and organization of this web. Standard cosmological models, based on general relativity and the current understanding of dark matter and dark energy, predict that structure formation proceeds hierarchically. Small structures form first, through the collapse of low-mass dark matter halos, and larger structures assemble later through mergers and accretion. This process is relatively slow, requiring hundreds of millions to billions of years to produce the large-scale filamentary structures observed in the local universe. The presence of such structures at redshifts, corresponding to less than a few 100 million years after the Big Bang, is difficult to reconcile with this timeline. Either structure formation began earlier than expected, or it proceeded more rapidly, or the observed structures are not as massive or extended as they appear. One possibility is that the density fluctuations in the early universe were larger than current models assume. If the initial perturbations were more pronounced, they would have collapsed more quickly, accelerating the formation of dark matter halos and, consequently, galaxies. However, the amplitude of these perturbations is constrained by observations of the cosmic microwave background, which reveal the statistical properties of density variations at the time of recombination. Any significant increase in the amplitude of fluctuations would alter the predicted power spectrum of the cosmic microwave background, potentially bringing it into conflict with observations. Another possibility is that dark matter behaves differently than assumed in standard models. Most cosmological simulations assume that dark matter is cold, meaning it consists of particles moving slowly compared to the speed of light, which allows it to collapse efficiently on small scales. If dark matter were warm or had additional interactions, it could affect the rate and scale of structure formation. However, there is currently no compelling evidence for such deviations, and warm dark matter models are constrained by a range of observations. A third possibility is that the observed structures are not as massive or as gravitationally bound as they appear. Galaxy clustering can arise from several mechanisms, not all of which require deep gravitational potential wells. For example, galaxies can appear clustered simply because they formed from gas clouds that were initially close together, even if they are not gravitationally bound into a stable structure. Such clustering would be transient, dissipating as the galaxies move apart over time. Additionally, projection effects can create the illusion of structure when galaxies at different distances happen to align along the same line of sight. Distinguishing between genuine three-dimensional structures and projection effects requires precise redshift measurements for each galaxy, which is observationally demanding but possible with Webb's spectroscopic capabilities. Early analyses suggest that at least some of the observed clustering is real, with galaxies sharing similar redshifts and thus occupying the same region of space, but further data is needed to confirm the extent and mass of the structures. Another factor to consider is the role of gravitational lensing. Massive structures, such as galaxy clusters, bend spacetime according to general relativity, deflecting the paths of light rays passing near them. This effect, known as gravitational lensing, can magnify and distort the images of background objects, making them appear brighter and larger than they would otherwise. Webb has used gravitational lensing to study high redshift galaxies, taking advantage of foreground galaxy clusters as natural telescopes. In some cases, the lensing effect can also create multiple images of the same background galaxy, or stretch it into an arc. If the hidden web of galaxies is located behind a massive foreground structure, lensing could enhance their detectability, but it could also distort their apparent distribution, making a relatively smooth distribution of galaxies appear more clumped or filamentary. Careful modeling of the lensing effect is required to reconstruct the true distribution of galaxies, and this is an active area of research. The discovery also has implications for the process of reionization. As the first stars and galaxies formed, they emitted ultraviolet radiation capable of ionizing neutral hydrogen. This radiation propagated outward from each galaxy, creating expanding bubbles of ionized gas. Over time, these bubbles overlapped and merged, eventually ionizing the entire universe. The timeline and topology of reionization depend on the spatial distribution of early galaxies. If galaxies were clustered into filaments and nodes, as the hidden web suggests, reionization would have proceeded in an inhomogeneous manner, with ionized regions forming first along the filaments and expanding outward into the surrounding neutral gas. This would create a patchy reionization topology, with islands of ionized gas separated by regions of neutral gas, gradually merging as more galaxies formed and emitted ionizing photons. Observational signatures of this process include variations in the ionization state of intergalactic gas as a function of position and redshift, which can be studied through the spectra of high-redshift quasars and galaxies. Webb's ability to detect faint galaxies at high redshifts provides critical data for understanding the sources of reionization and the evolution of the ionization state of the universe. The hidden Webb also intersects with questions about the role of supermassive black holes in early galaxy formation. Recent observations by Webb have revealed the presence of massive black holes, with masses exceeding 1 billion times that of the Sun, in galaxies observed less than 1 billion years after the Big Bang. The existence of such massive black holes at such early times is difficult to explain, as current models predict that black holes grow relatively slowly through accretion of gas and mergers with other black holes. If the hidden Webb represents regions of enhanced matter density, it could provide the conditions necessary for rapid black hole growth. High-density environments would supply abundant gas for accretion, and frequent galaxy mergers within the filaments could accelerate black hole growth through mergers of smaller black holes. Additionally, the gravitational potential wells associated with the filaments could funnel gas toward the centers of galaxies, further enhancing accretion rates. Testing this hypothesis requires correlating the positions of massive black holes with the structure of the Webb, which is an ongoing effort. The observational campaign to map the hidden Webb is far from complete. Webb's initial observations covered relatively small areas of the sky, providing only a glimpse of the larger structure. To fully characterize the Webb, astronomers need to observe larger regions and deeper exposures, accumulating more data on the positions, redshifts, and properties of high redshift galaxies. This requires significant telescope time, as each observation demands hours of exposure to detect the faintest galaxies. Coordinated surveys involving multiple observing programs are underway to build a comprehensive picture. Additionally, complementary observations at other wavelengths, such as radio and millimeter waves, can provide information about the gas and dust content of galaxies, as well as the distribution of intergalactic gas, further constraining the structure and evolution of the Webb. Theoretical modeling plays an equally important role. Cosmological simulations, which use supercomputers to evolve the distribution of dark matter and baryonic matter from initial conditions shortly after the Big Bang to the present day, provide predictions for the formation and evolution of cosmic structure. Comparing these predictions to Webb's observations allows astronomers to test the validity of cosmological models and identify areas where the models may need refinement. Early comparisons suggest that while simulations do predict filamentary structure at high redshifts, the observed structures may be more pronounced or more extensive than expected, hinting at possible discrepancies. Resolving these discrepancies will require both improved observations and more sophisticated simulations that account for additional physical processes, such as the effects of supernova feedback, black hole feedback, and magnetic fields, all of which can influence the distribution and behavior of gas in galaxies and in the intergalactic medium. The concept of a hidden Webb also prompts reflection on the nature of observational limits. Astronomy is fundamentally a historical science. When astronomers observe distant objects, they are not seeing them as they are now, but as they were when the light detected today left them. The further away an object is, the further back in time we see it. This means that observing the universe at different distances is equivalent to observing it at different times in its history, providing a direct window into cosmic evolution. However, this window is bounded by two horizons. The first is the particle horizon, corresponding to the farthest distance from which light could have traveled to us since the Big Bang, defining the edge of the observable universe. The second is the observational horizon, determined not by the age of the universe but by the sensitivity and capabilities of our instruments. Prior to Webb, the observational horizon was set by the Hubble Space Telescope and ground-based telescopes, which could detect galaxies out to redshifts of about 11 or 12, corresponding to times around 400 million years after the Big Bang. Webb has pushed this observational horizon closer to the particle horizon, revealing galaxies at redshifts of 13 or higher. The hidden Webb exists in the gap between these two horizons, a region that was always part of the observable universe in principle, but remained unobserved in practice. Understanding the physical properties of galaxies within the hidden Webb requires detailed analysis of their spectra. Spectroscopy reveals not only redshift, but also the chemical composition of galaxies, the ages of their stellar populations, the rates at which they are forming stars, and the presence of active galactic nuclei powered by supermassive black holes. The spectra of high redshift galaxies show emission lines from elements such as hydrogen, oxygen, carbon, and nitrogen produced in the atmospheres of massive stars and expelled into the interstellar medium through stellar winds and supernova explosions. The relative strengths of these emission lines provide information about the metallicity of the gas, the temperature and density of the ionized regions, and the hardness of the radiation field, all of which reflect the physical conditions within the galaxy. Early spectroscopic observations of galaxies in the hidden Webb suggest that they have relatively low metallicities, as expected for young galaxies that have not yet experienced many generations of star formation. However, some galaxies show evidence of surprisingly high metallicities or unusual abundance ratios, hinting at rapid chemical enrichment or contributions from massive stars that exploded as supernovae shortly after formation. The star formation rates of these galaxies are inferred from the intensity of emission lines, particularly the hydrogen alpha line and the ultraviolet continuum. High star formation rates imply that large quantities of gas are being converted into stars, which requires both abundant gas and efficient cooling mechanisms to allow the gas to collapse. The observed star formation rates in some of the hidden Webb galaxies are remarkably high, comparable to or exceeding those of the most active star-forming galaxies in the local universe, despite the much smaller sizes and masses of the high redshift galaxies. This suggests that star formation in the early universe was extremely efficient, perhaps due to the high densities and low metallicities of the gas, which favor cooling and collapse. Understanding the regulation of star formation in these environments is critical for explaining how galaxies grow and evolve over cosmic time. The sizes and morphologies of galaxies in the hidden Webb are also of interest. Galaxies at high redshifts tend to be smaller and more irregular than present-day galaxies, reflecting their youth and the ongoing processes of assembly and star formation. Webb's high resolution allows it to resolve the internal structure of some of these galaxies, revealing clumps of star formation, asymmetric shapes, and evidence of interactions or mergers. These observations provide insights into the mechanisms of galaxy growth. In the current paradigm, galaxies grow both through the smooth accretion of gas from the intergalactic medium and through mergers with other galaxies. At high redshifts, when galaxies were more closely spaced and the universe was denser, mergers were likely more frequent, contributing significantly to the buildup of stellar mass. The presence of disturbed morphologies and tidal features in some of the hidden Webb galaxies supports this picture, though the relative importance of mergers versus smooth accretion remains a topic of active research. The role of dark matter in shaping the hidden Webb cannot be overstated. Dark matter constitutes approximately 85% of the total matter in the universe, and its gravitational influence dominates the formation of structure. The distribution of dark matter at high redshifts can be inferred indirectly through several methods. One is gravitational lensing, as mentioned earlier, which measures the deflection of light by mass and thus maps the total mass distribution, including dark matter. Another is galaxy clustering, which traces the distribution of dark matter halos, since galaxies form within these halos and their clustering reflects the underlying dark matter distribution. A third method is the analysis of the cosmic microwave background, which records the imprint of density fluctuations at early times and provides initial conditions for structure formation. By combining these methods, astronomers can build a detailed picture of how dark matter is distributed at various redshifts and how it evolves over time. The hidden web, as revealed by Webb, represents the luminous component of a much larger and more massive dark matter web, invisible except through its gravitational effects. The concept of cosmic variance introduces an additional layer of complexity. Cosmic variance refers to the statistical uncertainty inherent in observations of a finite volume of the universe. Because the universe is not perfectly uniform, the properties of galaxies and structures measured in one region may differ from those measured in another, simply due to random fluctuations in the underlying density field. This is particularly relevant for observations of high redshift galaxies, which cover relatively small areas of the sky and thus sample limited volumes of space. The hidden web detected by Webb may represent an overdense region, a cosmic fluctuation that is more pronounced than average. Alternatively, it could be representative of the typical structure at those redshifts, but this can only be determined by observing multiple independent regions and comparing their properties. Surveys designed to minimize cosmic variance involve observing many widely separated fields, ensuring that the sample is representative of the universe as a whole. Another consideration is the potential for observational biases to influence the detected distribution of galaxies. For example, Webb's sensitivity varies with wavelength and with the brightness and size of objects. Faint, compact galaxies may be missed, while brighter or more extended galaxies are more easily detected. If the hidden web consists primarily of relatively bright galaxies, it would be more easily detected than regions populated by fainter galaxies, leading to a biased view of the true distribution. Correcting for such biases requires careful modeling of the selection function, which describes the probability of detecting a galaxy as a function of its properties and position. This modeling is essential for deriving accurate estimates of the abundance and clustering of galaxies at high redshifts. The discovery of the hidden web also has implications for the measurement of cosmological parameters. The abundance and clustering of galaxies at various redshifts depend on the properties of the universe, such as its expansion rate, its matter and energy content, and the amplitude of primordial density, fluctuations. By comparing observations to theoretical predictions, astronomers can constrain these parameters with increasing precision. The presence of structure at higher redshifts than expected, or with a different amplitude than predicted, could indicate the need to revise current estimates of these parameters or to modify the underlying cosmological model. For instance, if the hidden web is more extensive or more massive than models predict, it could imply that the matter density of the universe is higher than currently thought, or that the amplitude of density fluctuations is larger, or that dark energy behaves differently than assumed. Disentangling these possibilities requires careful analysis of multiple independent datasets, including observations of the cosmic microwave background, the large-scale distribution of galaxies at lower redshifts, and the expansion history of the universe measured through supernova and baryon acoustic oscillation surveys. The timeline of observations that led to the discovery of the hidden web began with Webb's commissioning phase, during which the telescope's instruments were tested and calibrated. Among the first science observations were deep field images targeting regions of the sky previously studied by Hubble, allowing for direct comparisons and assessments of Webb's superior capabilities. The Hubble Ultra Deep Field, for example, had been observed for hundreds of hours, revealing thousands of galaxies at various redshifts. When Webb observed the same region, it not only detected the galaxies already known from Hubble, but also revealed many additional galaxies, fainter and redder, that had been missed. Some of these newly detected galaxies were at moderate redshifts, but others were at the very highest redshifts, beyond the reach of Hubble. It was in these populations of newly detected high redshift galaxies that the first hints of the hidden Webb emerged. Astronomers noticed that the galaxies were not randomly distributed, but showed coherent spatial patterns, with alignments and clustering suggestive of large-scale structure. Follow-up observations targeted additional fields, including regions of the sky that had not been previously studied in depth. These observations confirmed that the phenomenon was not unique to a single field, but appeared to be a general feature of the high redshift universe. Spectroscopic observations were then conducted to measure precise redshifts for a subset of the galaxies, confirming that they were indeed at the high redshifts inferred from photometry and that they shared common redshifts, indicating that they occupied the same regions of space. These confirmations solidified the interpretation that the observed patterns represented real three-dimensional structures rather than projection effects or artifacts. The role of Webb's mid-infrared instrument deserves particular attention. While the near-infrared camera is optimized for detecting galaxies at moderately high redshifts, the mid-infrared instrument extends Webb's reach to even longer wavelengths, allowing it to detect galaxies at the very highest redshifts and to study the dust content of galaxies across cosmic time. Dust, composed of small solid particles formed in the atmospheres of evolved stars and in supernova ejecta, absorbs ultraviolet and optical light and re-emits it at infrared wavelengths. Dusty galaxies, which are common in the local universe and at intermediate redshifts, are thus brightest in the infrared. At high redshifts, the presence of dust can obscure the ultraviolet light from young stars, making galaxies appear fainter in the optical and near-infrared, but brighter in the mid-infrared. Webb's mid-infrared instrument can detect this emission, revealing dusty, star-forming galaxies that would otherwise be missed. Some of the galaxies in the hidden Webb show significant mid-infrared emission, indicating the presence of dust and suggesting that star formation in the early universe was not always pristine, but could be accompanied by substantial dust production, even at very early times. The interplay between star formation, supernova feedback, and chemical enrichment is central to understanding the properties of the hidden Webb galaxies. When massive stars reach the end of their lives, they explode as supernovae, releasing vast amounts of energy and ejecting heavy elements into the surrounding gas. This process, known as feedback, can heat and disperse the gas, suppressing further star formation, or it can compress the gas, triggering new star formation. The balance between these effects depends on the mass of the galaxy, the rate of star formation, and the efficiency with which energy is deposited into the gas. In small, low-mass galaxies, supernova feedback can drive strong outflows that eject gas from the galaxy entirely, reducing the fuel available for star formation and limiting the growth of the galaxy. In larger, more massive galaxies, the deeper gravitational potential well can retain the gas, allowing star formation to continue despite the feedback. The hidden Webb galaxies span a range of masses, and their properties reflect these varying feedback efficiencies. Some show evidence of strong outflows, with broad emission lines indicative of high-velocity gas, while others appear more quiescent, with narrow lines suggesting that the gas remains bound within the galaxy. Chemical enrichment proceeds in tandem with star formation. Each generation of stars produces heavy elements, increasing the metallicity of the interstellar medium. The metallicity of a galaxy thus provides a record of its star formation history, with higher metallicities indicating more prolonged or intense star formation. The metallicities of the hidden Webb galaxies, as inferred from their spectra, are generally low, consistent with their youth, but there is considerable variation. Some galaxies have metallicities only a few percent of the solar value, while others approach 10 or 20%. This variation may reflect differences in star formation efficiency, in the retention or expulsion of metals by feedback, or in the inflow of pristine gas from the intergalactic medium, which would dilute the metal content. Understanding this variation is key to reconstructing the detailed histories of individual galaxies and the evolution of the galaxy population as a whole. The detection of the hidden web also underscores the importance of synergy between space-based and ground-based observatories. While Webb provides unparalleled sensitivity and resolution in the infrared, ground-based telescopes equipped with adaptive optics and large collecting areas can complement Webb's observations by providing wider field-of-view imaging and spectroscopy, as well as observations at optical and near-infrared wavelengths where Earth's atmosphere is more transparent. Radio and millimeter observatories, such as the Atacama Large Millimeter Array, can detect the emission from cold gas and dust, tracing the raw material for star formation and providing a different perspective on the structure of the web. X-ray observatories can detect emission from hot gas in galaxy clusters and from active galactic nuclei, revealing the high-energy processes associated with structure formation. The combination of data from multiple observatories, each sensitive to different physical processes and different wavelength regimes, provides a more complete understanding of the hidden web than any single observatory could achieve alone. The philosophical implications of the discovery extend beyond the technical details. The hidden web challenges the notion of a simple, hierarchical buildup of structure, suggesting instead a more complex and interconnected process. It raises questions about the degree to which the universe's large-scale structure was predetermined by initial conditions versus shaped by stochastic processes such as mergers and feedback. It also highlights the limits of human knowledge and the vastness of the unexplored. Despite centuries of astronomical observation and decades of space-based telescopy, vast regions of the universe remained unseen until Webb's deployment. This serves as a reminder that the observable universe is not synonymous with the observed universe, and that each new instrument reveals previously hidden layers of reality. The hidden web is not the final frontier, but one of many, and future instruments will undoubtedly reveal structures and phenomena that are currently beyond even Webb's reach. The technological achievement represented by Webb is itself a subject worthy of consideration. The telescope is the result of decades of planning, engineering, and testing, involving contributions from thousands of scientists and engineers across multiple countries. Its primary mirror is composed of 18 hexagonal segments, each made of beryllium and coated with gold to maximize infrared reflectivity. These segments were folded during launch to fit within the payload fairing of the rocket and then deployed and precisely aligned in space, a process requiring micron-level accuracy. The telescope's sun shield, a 5-layer structure the size of a tennis court, protects the instruments from the heat of the sun, Earth, and Moon, maintaining the mirror and instruments at temperatures below 50 Kelvin, necessary for infrared sensitivity. The instruments themselves incorporate advanced detectors and dispersive elements, capable of measuring faint signals across a wide range of wavelengths with high precision. The successful deployment and operation of Webb represents one of the most complex engineering projects ever undertaken, and its scientific return justifies the investment. The data collected by Webb is not analyzed in isolation, but is integrated into a broader framework of cosmological knowledge. The cosmic microwave background, observed by missions such as Planck and the Wilkinson Microwave Anisotropy Probe, provides a snapshot of the universe at a redshift of approximately 1,100, when it was only 380,000 years old. The temperature fluctuations in the cosmic microwave background reveal the initial density fluctuations that seeded structure formation, and their statistical properties constrain the parameters of the cosmological model. The large-scale distribution of galaxies at low and intermediate redshifts, mapped by surveys such as the Sloan Digital Sky Survey and the Dark Energy Survey, traces the evolved cosmic web and provides measurements of the expansion history and growth of structure. The hidden web detected by Webb fills in a critical gap between these two regimes, connecting the initial conditions imprinted in the cosmic microwave background to the mature structures observed in the local universe. By comparing the properties of the hidden web to predictions derived from the cosmic microwave background and to observations of the low redshift cosmic web, astronomers can test the consistency of the cosmological model across cosmic time and identify any deviations that might point to new physics. One of the key predictions of cosmological models is the correlation function, a statistical measure that describes the probability of finding galaxies separated by a given distance. In a universe where structure forms hierarchically from small scales to large scales, the correlation function evolves in a predictable way, with the amplitude of clustering increasing over time as gravity amplifies the initial density fluctuations. The correlation function of the hidden web galaxies can be measured by analyzing their spatial distribution and comparing this to the predicted correlation function at the corresponding redshift tests the accuracy of the models. Early measurements suggest that the clustering amplitude of the hidden web galaxies may be higher than expected, though uncertainties remain due to the limited sample size and the challenges of accurately measuring distances at high redshifts. If confirmed, a higher-than-expected clustering amplitude could indicate that either the initial density fluctuations were larger than inferred from the cosmic microwave background, or that the growth of structure proceeded more rapidly, perhaps due to modifications of gravity or the properties of dark matter. The discovery of the hidden web also intersects with efforts to understand dark energy, the mysterious component that drives the accelerated expansion of the universe. Dark energy is inferred from observations showing that the expansion of the universe is speeding up rather than slowing down, as would be expected if gravity were the only significant force acting on cosmic scales. The nature of dark energy is one of the most profound unsolved problems in physics, with candidates ranging from a cosmological constant, a form of energy intrinsic to space itself, to dynamical fields that vary over time and space. The growth of cosmic structure is sensitive to the properties of dark energy because the rate at which structure forms depends on the expansion history of the universe, which in turn depends on the energy content and equation of state of dark energy. By measuring the abundance and clustering of galaxies at various redshifts, including the high redshift galaxies in the hidden web, astronomers can constrain the equation of state of dark energy and test whether it is consistent with a cosmological constant or whether more exotic models are required. The hidden web also provides a laboratory for studying the physics of the intergalactic medium, the diffuse gas that fills the space between galaxies. At high redshifts, the intergalactic medium is composed primarily of hydrogen and helium, with trace amounts of heavier elements ejected from galaxies by supernovae and stellar winds. The ionization state of the intergalactic medium depends on the balance between ionizing radiation from stars and quasars and recombination processes that convert ionized gas back to neutral gas. During the epoch of reionization, the intergalactic medium transitioned from predominantly neutral to predominantly ionized, driven by the ultraviolet radiation from the first galaxies. The presence of the hidden web, with its high density of galaxies, suggests that these regions were among the first to be ionized, creating ionized bubbles that expanded and eventually merged. The topology and evolution of these bubbles can be studied through observations of the Lyman alpha emission from high redshift galaxies, which is absorbed by neutral hydrogen along the line of sight, and through observations of the spectra of distant quasars, which show absorption features corresponding to intergalactic hydrogen at various redshifts. Webb's spectroscopic capabilities enable detailed studies of the Lyman alpha emission and absorption, providing insights into the reionization process and the properties of the intergalactic medium. The detection of the hidden web has also prompted new theoretical work on the nature of the first galaxies. In standard models, the first stars, known as population 3 stars, formed from pristine gas composed only of hydrogen and helium, with no heavy elements. These stars were likely very massive, with masses tens or hundreds of times that of the Sun, and they burned brightly but briefly, ending their lives in powerful supernova explosions that enriched the surrounding gas with the first heavy elements. The subsequent generation of stars, known as population 2 stars, formed from this enriched gas, and these are the stars that populate the galaxies observed today. The hidden Webb galaxies are likely composed of population 2 stars, but the possibility remains that some population 3 stars could still exist in the earliest galaxies, or that their signatures could be detected through their effects on the spectra of their host galaxies. Detecting population 3 stars would provide direct evidence of the first generation of stellar nucleosynthesis and would constrain models of early star formation. The role of magnetic fields in the formation and evolution of the hidden Webb is an emerging area of research. Magnetic fields are ubiquitous in the universe, present in stars, galaxies, galaxy clusters, and the intergalactic medium. They are thought to be generated and amplified by dynamo processes, in which the motion of charged particles in ionized gas generates electrical currents that produce magnetic fields. In the early universe, the origin of the seed magnetic fields that were subsequently amplified by dynamos is uncertain, with proposed mechanisms including generation during phase transitions in the early universe, production by the first stars and black holes, or injection by cosmic rays. The strength and structure of magnetic fields can influence the formation of galaxies by affecting the dynamics of gas, either by providing additional pressure support against gravitational collapse or by facilitating the transport of angular momentum, allowing gas to fall toward the centers of galaxies. Magnetic fields can also affect the propagation of cosmic rays, which are high-energy particles produced in supernova explosions and other energetic events, and which can heat the interstellar and intergalactic medium, further influencing star formation. Measuring the strength and structure of magnetic fields at high redshifts is observationally challenging, requiring sensitive radio observations that can detect the polarized emission from synchrotron radiation, which is produced by relativistic electrons spiraling in magnetic fields. Such observations are beyond Webb's capabilities, but are possible with radio telescopes such as the Square Kilometre Array, which is currently under construction. The discovery of the hidden Webb has implications for the search for life in the universe. The conditions necessary for life, as currently understood, include the presence of liquid water, a source of energy, and the availability of chemical elements necessary for building complex molecules. These conditions are most likely to be met on planets orbiting stars within galaxies, and the abundance and properties of galaxies thus influence the overall probability of life emerging in the universe. The hidden Webb, by revealing a large population of galaxies at very early times, suggests that the conditions for life may have been present much earlier in cosmic history than previously thought. However, the high redshift galaxies are also likely to be more hostile environments than present-day galaxies, with higher rates of supernova explosions, more intense radiation fields, and potentially less stable planetary systems due to the higher frequency of interactions and mergers. Whether life could have emerged in such environments, or whether the early universe was too turbulent and short-lived for complex chemistry to develop, remains an open question. Webb's observations provide data on the physical conditions in the early universe, but addressing the question of life requires integration of this data with models of planetary formation, atmospheric chemistry, and the origins of life, all of which are active areas of research. The hidden Webb also serves as a reminder of the importance of long-term planning and investment in basic science. The development of Webb took more than 2 decades and cost billions of dollars, an investment that was justified by the potential for transformative discoveries. The discovery of the hidden Webb is one such discovery, but it is far from the only scientific return from Webb. The telescope has also provided detailed observations of exoplanet atmospheres, revealing the composition and structure of worlds orbiting other stars. It has imaged the inner regions of protoplanetary disks, where planets are forming. It has studied the molecular clouds where stars are born, resolving the densest cores and the outflows driven by young stars. It has observed the centers of galaxies, revealing the interplay between supermassive black holes and their host galaxies. And it has detected and characterized a variety of transient phenomena, including supernovae, gamma-ray burst afterglows, and gravitational lensing events. Each of these areas of research benefits from Webb's unique capabilities, and each contributes to a deeper understanding of the universe. The process of scientific discovery is itself worth reflecting upon. The detection of the hidden Webb was not the result of a single observation or a single insight, but emerged gradually from the accumulation and analysis of data, the comparison of observations to theoretical predictions, and the collaborative efforts of a global community of astronomers. The initial detections were tentative, subject to uncertainties and potential alternative explanations. It was only through repeated observations, careful statistical analysis, and the confirmation of predictions that the discovery solidified. This process is characteristic of modern astronomy, in which discoveries are rarely eureka moments, but instead result from the painstaking work of many individuals over many years. The tools and techniques used in this process, photometry, spectroscopy, statistical analysis, theoretical modeling, are the product of centuries of development, building on the work of countless scientists who developed the mathematical and physical frameworks that underpin our understanding of the universe. The hidden Webb also highlights the interplay between observation and theory in cosmology. Theoretical models provide predictions that guide observations, suggesting where to look and what to look for, but observations in turn constrain and refine the models, revealing discrepancies that prompt new theoretical developments. This iterative process drives progress in the field. The discovery of the hidden Webb was made possible by theoretical predictions that structure should exist at high redshifts, but the detailed properties of the observed structures, such as their extent, their galaxy densities, and their redshift distributions, were not fully anticipated by the models, prompting theorists to revisit their assumptions and explore new scenarios. This feedback loop between observation and theory is essential for advancing knowledge, and it is one of the defining features of cosmology as a science. The implications of the hidden Webb extend to the philosophy of science and epistemology, the study of knowledge and how it is acquired. The hidden Webb challenges the notion of a fixed and knowable universe, revealing that our understanding is always provisional and subject to revision in light of new observations. The universe is not a static object to be catalogued but a dynamic and evolving system, and our knowledge of it is similarly dynamic. Each new observation adds to the body of knowledge but also opens new questions and reveals new layers of complexity. The hidden Webb, in this sense, is both an answer and a question. It reveals the presence of structure at high redshifts, but it also raises questions about how that structure formed, what it implies for cosmological models, and what other structures might exist beyond the reach of current instruments. This perpetual expansion of knowledge in which each answer generates new questions is characteristic of science and is a source of both humility and inspiration. The discovery of the hidden Webb also has practical implications for future missions. It demonstrates the value of large space-based telescopes optimized for infrared observations, validating the investment in Webb and providing a template for future instruments. Concepts for next-generation space telescopes, such as the Habitable Worlds Observatory, or a successor to Webb with even larger mirrors and more sensitive detectors, are informed by the successes and limitations of Webb. The hidden Webb's detection suggests that there are still fainter and more distant galaxies waiting to be discovered, and that future instruments will need even greater sensitivity and resolution to detect them. Additionally, the discovery underscores the importance of wide-field surveys, which can map large areas of the sky and provide statistical samples of galaxies across a range of redshifts, and the importance of spectroscopic follow-up, which provides detailed information about individual galaxies and confirms photometric redshift estimates. The role of international collaboration in the success of Webb and the discovery of the hidden Webb is also significant. Webb is a joint project of NASA, the European Space Agency, and the Canadian Space Agency, with contributions from institutions in many countries. The construction, testing, and operation of the telescope required coordination across multiple continents and the integration of diverse expertise in optics, cryogenics, detector technology, software development, and spacecraft engineering. The analysis of Webb's data similarly involves international teams of astronomers working together to interpret observations, develop models, and publish results. This collaborative model is increasingly common in large-scale science projects, driven by the complexity and cost of the instruments and by the recognition that the most challenging scientific questions require diverse perspectives and skills. The discovery of the hidden Webb is a testament to the power of international cooperation and the shared human endeavor to understand the cosmos. The hidden Webb also intersects with broader cultural and societal themes. Astronomy has long been a source of wonder and inspiration, providing perspectives that transcend daily concerns and connect individuals to the larger cosmos. The images returned by Webb, with their stunning detail and beauty, have captured the public imagination, appearing in media outlets around the world and sparking conversations about humanity's place in the universe. The hidden Webb, as a newly revealed layer of cosmic structure, adds to this sense of wonder, reminding us that the universe is far more intricate and vast than we can easily comprehend. At the same time, the discovery underscores the value of scientific inquiry and the importance of supporting research that may not have immediate practical applications, but that expands the boundaries of knowledge and enriches our understanding of existence. The hidden Webb also raises questions about the limits of human perception and cognition. The structures detected by Webb are not accessible to direct human senses. They are revealed only through the mediation of instruments and the interpretation of data. The light from these galaxies has been traveling for more than 13 billion years, and the galaxies themselves, as they exist now, are forever beyond our reach, their current state unobservable due to the finite speed of light and the expansion of space. This introduces a fundamental asymmetry in our relationship to the cosmos. We can observe the past but not the present of distant objects, and the most distant objects we observe are those whose light has had the most time to reach us, which are also the objects that emitted their light in the earliest epochs of the universe. The hidden Webb thus represents a snapshot of the universe's infancy, frozen in time by the journey of light across the expanding cosmos. Understanding this snapshot requires reconstructing the physical conditions and processes that prevailed at that time, a task that demands both observational data and theoretical modeling. The detection methods used to identify the hidden Webb rely on the redshift distance relation, a fundamental result of cosmology that links the redshift of an object to its distance and to the time at which the observed light was emitted. This relation depends on the expansion history of the universe, which in turn depends on the content and properties of the universe, its matter, dark energy, and curvature. The expansion history is described by the Hubble parameter, which quantifies the rate of expansion as a function of time, and by the scale factor, which describes how distances between objects grow as the universe expands. The redshift of a galaxy is determined by the ratio of the scale factor at the time of emission to the scale factor at the time of observation. For distant galaxies, the observed wavelength of light is significantly longer than the emitted wavelength, resulting in large redshift values. The most distant galaxies in the hidden Webb have redshifts exceeding 13, meaning that the universe has expanded by a factor of more than 14 since the light was emitted. This expansion has stretched not only the wavelength of the light but also the spatial distribution of matter, so that structures that appeared close together at early times are now separated by vast distances. The process of measuring redshifts involves identifying spectral features with known rest frame wavelengths and comparing the observed wavelengths of these features to their rest frame values. Common features used for redshift determination include emission lines from hydrogen, oxygen, and other elements, as well as absorption features such as the Lyman break. For very distant galaxies, many of these features are shifted out of the optical range and into the infrared, which is why Webb's infrared sensitivity is critical. Spectroscopic redshifts, obtained by dispersing the light into a spectrum, are more accurate than photometric redshifts, which are estimated from multiband imaging, but they require longer exposure times and are thus more time-consuming. The combination of photometric and spectroscopic redshifts is often used, with photometric redshifts providing initial candidates and spectroscopic redshifts providing confirmation and detailed information. The physical interpretation of redshift involves both cosmological expansion and, in some cases, peculiar velocities, which are the motions of galaxies relative to the overall expansion flow due to gravitational interactions with nearby structures. For the most distant galaxies, peculiar velocities are negligible compared to the cosmological redshift, but for galaxies at intermediate redshifts, peculiar velocities can introduce small corrections to the inferred distances. These corrections are important for precise measurements of the large-scale structure and for inferring the masses of galaxy clusters and the distribution of dark matter. The hidden Webb's existence also prompts consideration of the concept of causality in cosmology. The universe has a causal horizon, defined by the distance that light can have traveled since the Big Bang. Objects separated by more than this distance could not have influenced each other, as no signal traveling at the speed of light could have passed between them. The large-scale structure of the universe, including the hidden Webb, formed from density fluctuations that were causally connected at very early times before inflation. Inflation, a hypothesized period of exponential expansion in the first fraction of a second after the Big Bang, stretched quantum fluctuations to macroscopic scales and created the initial density perturbations. These perturbations were causally connected before inflation, but after inflation they were spread across regions that became causally disconnected, explaining the uniformity of the cosmic microwave background and the coherence of large-scale structure. The hidden Webb is thus a product of processes that occurred at the very beginning of the universe, amplified by gravitational instability over billions of years. The observational challenges associated with detecting the hidden Webb are formidable. High redshift galaxies are extremely faint, requiring long exposures to collect sufficient photons for detection. Even with Webb's sensitivity, some galaxies are detected with only a handful of photons, making the measurements subject to statistical noise. Additionally, the sky is not perfectly dark. It contains foreground emission from zodiacal light, the glow from dust in the solar system, and from faint unresolved background galaxies. Subtracting these foregrounds requires careful modeling and calibration. Cosmic rays, high-energy particles from space, can strike the detectors and create spurious signals that must be identified and removed. Instrumental artifacts, such as scattered light and detector noise, can also mimic faint galaxies, requiring rigorous criteria for distinguishing real objects from noise. All of these challenges are addressed through sophisticated data processing pipelines that combine multiple exposures, correct for instrumental effects, and apply statistical filters to identify real sources. The discovery of the hidden Webb has also stimulated interest in the role of baryonic physics in structure formation. While dark matter provides the gravitational scaffolding for structure, baryonic matter, the ordinary matter that makes up stars, gas, and planets, behaves differently due to its electromagnetic interactions. Baryonic matter can cool through radiation, allowing it to collapse into denser structures than dark matter, which cannot cool. This cooling is mediated by atomic and molecular processes, such as the emission of photons by excited atoms and molecules. The efficiency of cooling depends on the metallicity of the gas. Higher metallicity gas can cool more efficiently because heavy elements provide additional emission lines. In the early universe, when metallicities were low, cooling was less efficient, potentially slowing the formation of stars and galaxies. However, the presence of the hidden Webb, with its evidence of significant star formation at very early times, suggests that cooling was nonetheless effective, possibly due to the high densities of gas in the collapsing dark matter halos or to the role of molecular hydrogen, which can provide cooling even in the absence of heavy elements. Understanding the detailed baryonic physics of early galaxy formation requires sophisticated hydrodynamic simulations that model the behavior of gas, star formation, and feedback processes. The potential for gravitational waves to provide complementary information about the early universe is an exciting frontier. Gravitational waves are ripples in spacetime produced by accelerating masses, predicted by general relativity, and first detected directly in 2015 by the LIGO Observatory. While current detectors are sensitive to gravitational waves from stellar mass black hole and neutron star mergers, future detectors, such as the Laser Interferometer Space Antenna, will be sensitive to lower frequency gravitational waves from supermassive black hole mergers and from cosmological sources. The mergers of galaxies and black holes in the hidden Webb, if they occurred in sufficient numbers, could produce a background of gravitational waves that might be detectable, providing an independent probe of the structure and evolution of the early universe. Additionally, gravitational waves from the early universe itself, such as those produced by inflation or phase transitions, could provide information about the initial conditions that gave rise to the density fluctuations observed in the cosmic microwave background and traced by the hidden Webb. The discovery of the hidden Webb also connects to ongoing debates about the nature of time and the age of the universe. The age of the universe, currently estimated at approximately 13.8 billion years, is determined from measurements of the expansion rate and the matter and energy content of the universe, combined with the assumption that general relativity accurately describes gravity on cosmic scales. This age is consistent with the ages of the oldest stars and with the time since the Big Bang inferred from the cosmic microwave background. However, some observations, such as the existence of massive galaxies and supermassive black holes at very high redshifts, have prompted questions about whether the universe could be older than currently estimated, or whether the early phases of structure formation proceeded more rapidly than models predict. The hidden Webb adds to these questions by revealing extensive structure at times less than a few hundred million years after the Big Bang. Resolving these questions will require more precise measurements of the expansion history and the ages of high redshift objects, as well as refinements to models of structure formation. The role of neutrinos, elusive particles that interact only weakly with matter, is another subtle but important factor in cosmology. Neutrinos are produced in vast numbers in the Big Bang and in stellar processes, and they contribute to the energy content of the universe. Although their individual masses are very small, their cumulative mass is sufficient to affect the formation of large-scale structure. Massive neutrinos stream freely through the universe at relativistic speeds, smoothing out small-scale density fluctuations and suppressing the growth of structure on certain scales. The effect of neutrinos on structure formation depends on their total mass, which is constrained by cosmological observations, including the clustering of galaxies and the cosmic microwave background. The hidden Webb, by providing data on the abundance and clustering of galaxies at high redshifts, contributes to these constraints, helping to determine the masses of neutrinos and their role in cosmic evolution. The discovery also has implications for the concept of cosmic horizons and the ultimate fate of the universe. The observable universe is bounded by the particle horizon, beyond which objects are receding faster than the speed of light due to the expansion of space, and light from these objects can never reach us. As the universe continues to expand, driven by dark energy, distant galaxies will cross the cosmological event horizon, the boundary beyond which objects are receding at the speed of light, and they will fade from view as their light is redshifted to ever longer wavelengths and diluted by the expansion. In the far future, if dark energy remains constant, the universe will become increasingly empty from the perspective of any given observer, with only the galaxies in the local gravitational group remaining visible. The hidden Webb, observed at the edge of the current observable universe, represents structures that are already close to this horizon, and in the deep future, analogous structures forming at even earlier times will be forever beyond the reach of any observer. This underscores the fleeting nature of our observational window and the importance of making the most of current capabilities. The hidden Webb's discovery is also a case study in the power of technological innovation to transform science. The leap in capability from Hubble to Webb is analogous to the leap from early optical telescopes to Hubble itself, each new generation of instruments revealing phenomena that were previously invisible. The development of sensitive infrared detectors, large deployable mirrors, and cryogenic cooling systems has enabled Webb to achieve its extraordinary performance, and future advances in these and other technologies will continue to push the boundaries of what is observable. The trajectory of astronomical technology suggests that within the coming decades, even larger and more sensitive telescopes will be built, both in space and on the ground, and these instruments will reveal still fainter and more distant objects, perhaps detecting the very first stars and galaxies, or even probing the universe at times before the first stars formed, when only the glow of the cosmic microwave background illuminated the cosmos. The hidden Webb also serves as a focal point for interdisciplinary collaboration. Astronomers work not only with physicists but also with mathematicians, who develop the statistical and computational methods needed to analyze large data sets, with engineers, who design and build the instruments and spacecraft, with computer scientists, who develop the software and algorithms for data processing and simulation, and with educators and communicators, who share the discoveries with the public and inspire the next generation of scientists. The complexity of modern astronomy requires contributions from all of these fields, and the success of projects like Webb depends on the effective integration of diverse expertise. The discovery of the hidden Webb has also generated excitement in the broader scientific community, as it provides new constraints on models of galaxy formation and evolution that are relevant to multiple areas of astrophysics. For example, understanding the formation of the first galaxies informs models of star formation, which are relevant to studies of nearby galaxies and molecular clouds. Understanding the role of supermassive black holes in early galaxies informs models of accretion and jet formation, which are relevant to studies of active galactic nuclei and gamma-ray bursts. Understanding the chemical enrichment of the early universe informs models of nucleosynthesis, which are relevant to studies of stellar evolution and the origin of the elements. In this way, the discovery of the hidden Webb resonates across many subfields of astronomy and contributes to a more comprehensive understanding of the universe. The hidden Webb also raises questions about the universality of physical laws. The observations of high-redshift galaxies probe the universe under conditions very different from those in the local universe: higher densities, higher temperatures, lower metallicities, and stronger radiation fields. Testing whether the laws of physics, as understood from experiments and observations in the local universe, apply equally at these early times and extreme conditions is an important goal of cosmology. So far, all observations are consistent with the universality of physical laws, but the discovery of unexpected phenomena, such as the more extensive structure of the hidden Webb, prompts careful examination of whether standard models fully capture the physics or whether new effects need to be considered. The concept of the hidden web also relates to the idea of the cosmic frontier, the boundary between what is known and what remains to be discovered. Throughout history, astronomy has been characterized by the exploration of new frontiers. First the planets, then the stars, then the galaxies, and now the early universe and the large-scale structure of spacetime. Each frontier has revealed new phenomena and raised new questions, driving the development of new theories and new technologies. The hidden web represents the current frontier, the edge of observational capability, and its exploration is revealing a universe that is more structured, more dynamic, and more complex than previously imagined. Future frontiers will include the direct detection of dark matter particles, the characterization of exoplanet atmospheres for signs of life, the observation of the first stars, and perhaps the detection of gravitational waves from the Big Bang itself. Each of these frontiers promises transformative discoveries that will reshape our understanding of the cosmos. The hidden web also has resonance with the history of astronomy, echoing earlier discoveries that revealed previously hidden structures. The discovery of galaxies beyond the Milky Way in the early 20th century, for example, fundamentally changed our understanding of the scale of the universe, revealing that the Milky Way was just one of countless galaxies scattered across space. The discovery of the expansion of the universe through the observation of redshifts of distant galaxies revealed that the universe is not static but dynamic, evolving over time. The discovery of the cosmic microwave background provided direct evidence for the Big Bang and opened the field of observational cosmology. The discovery of dark matter and dark energy revealed that the majority of the universe's content is invisible and fundamentally different from ordinary matter. The hidden web is the latest in this series of revelations, each of which has expanded the scope of astronomy and deepened our understanding of the cosmos. The discovery also highlights the role of serendipity in science. While Webb was designed with the goal of observing high redshift galaxies, the specific discovery of an extensive web of galaxies at such early times was not necessarily anticipated. Many of the most important scientific discoveries have occurred not as the result of testing a specific hypothesis, but through the unexpected observations that arise when new instruments open new observational windows. The history of astronomy is replete with examples of serendipitous discoveries: pulsars, gamma-ray bursts, quasars, the cosmic microwave background itself, all of which were unexpected and all of which led to new areas of research. The hidden web may be such a discovery, and its implications may extend beyond current understanding, prompting new theoretical frameworks and new lines of inquiry. The hidden web also serves as a reminder of the importance of patience and persistence in science. The development of Webb spanned decades, involving setbacks, delays, and technical challenges, but the commitment to the project persisted, driven by the conviction that the scientific return would justify the investment. The analysis of Webb's data is similarly demanding, requiring careful attention to detail, rigorous statistical methods, and the willingness to revisit assumptions and interpretations in light of new evidence. The discovery of the hidden web is the result of this sustained effort, and it exemplifies the value of long-term commitment to fundamental research. The hidden web also intersects with questions about the role of computation in modern astronomy. The analysis of Webb's data involves processing terabytes of information, applying complex algorithms to correct for instrumental effects, and running large-scale simulations to compare observations to theoretical predictions. These tasks require powerful computers and sophisticated software, and the development of computational tools has become an integral part of astronomical research. The discovery of the hidden web was made possible not only by Webb's hardware, but also by the software pipelines that process its data, and by the simulations that provide context for interpreting the observations. As datasets grow larger and more complex, The role of computation in astronomy will continue to expand, and advances in machine learning, artificial intelligence, and high-performance computing will play an increasingly important role in enabling discoveries. The discovery of the hidden web also prompts reflection on the limits of language and metaphor in describing the universe. Terms like web, hidden, behind, and frontier are anthropocentric, drawn from human experience and applied to phenomena that operate on scales and timescales far beyond human intuition. A web suggests intentional design or biological structure, yet the cosmic web is purely the result of gravitational processes operating on dark matter and baryonic matter. Hidden implies concealment, yet the galaxies were not hidden in any intentional sense. They were simply too faint and too distant for previous instruments to detect. Behind suggests spatial location, yet in cosmology it refers to observational access rather than physical position. These metaphors are useful for communication and for framing the phenomena in familiar terms, but they can also mislead if taken too literally. The challenge for scientists and communicators is to use language that is evocative and accessible while remaining faithful to the underlying physics and avoiding implications that are not supported by observation. The hidden web also has implications for the sociology of science, the study of how scientific communities organize, collaborate, and produce knowledge. The discovery of the hidden web involved hundreds of astronomers from institutions around the world, each contributing specialized expertise. Decisions about observing targets, data processing methods, and publication strategies were made through collaborative processes, often involving extensive discussion and debate. The allocation of telescope time, the standards for data quality, and the criteria for authorship on scientific papers are all governed by norms and practices that have evolved over time within the astronomical community. Understanding these social dimensions of science is important for appreciating how discoveries are made and disseminated, and for identifying ways to improve the efficiency and inclusiveness of the research process. The hidden web also raises ethical questions about the use of resources and the priorities of scientific research. The cost of building and operating Webb is substantial, and some have questioned whether these resources could be better spent on other societal needs, such as healthcare, education, or addressing climate change. Advocates for astronomy argue that the pursuit of knowledge is intrinsically valuable, that astronomy inspires and educates, and that technological advances driven by space missions often have broader applications. The discovery of the hidden web, by revealing fundamental aspects of the universe's structure and history, contributes to this argument, demonstrating the scientific return on investment in space-based observatories. However, these debates highlight the need for transparency, accountability, and public engagement in decisions about large-scale scientific projects. The hidden web also connects to questions about the nature of reality and the relationship between observation and existence. In quantum mechanics, the act of observation plays a fundamental role, with the state of a system not fully determined until it is measured. In cosmology, while the universe exists independently of observation, our knowledge of it is entirely mediated by observation, and in a practical sense, the observable universe is the only universe we can study. The hidden web existed before it was detected, but it became part of scientific knowledge only through Webb's observations. This raises philosophical questions about the extent to which the universe is knowable, the role of the observer in constructing scientific understanding, and the relationship between the map and the territory, between our models of the universe and the universe itself. The discovery of the hidden web also has implications for science education and public outreach. Astronomy has a unique capacity to engage the public imagination, and discoveries like the hidden web provide opportunities to communicate the excitement of scientific research and the importance of continued investment in science. Educational programs, planetarium shows, documentaries, and online content can leverage Webb's images and the story of the hidden web to teach concepts in physics, cosmology, and the scientific method. By making the discovery accessible and engaging, scientists and educators can inspire students to pursue careers in science and technology, and can foster a broader appreciation for the role of science in society. The hidden web also underscores the interconnectedness of different areas of physics. The study of the early universe draws on general relativity, quantum mechanics, thermodynamics, nuclear physics, atomic physics, and particle physics, all of which contribute to our understanding of how matter and radiation behave under extreme conditions. The formation of structure involves gravitational dynamics, hydrodynamics, radiative transfer, and magnetic fields. The detection of high-redshift galaxies requires knowledge of optics, detector physics, signal processing, and statistical inference. The hidden web is thus not only a cosmological discovery but also a demonstration of the unity of physics and the power of applying fundamental principles to understand complex phenomena. The discovery also has implications for the concept of emergence in complex systems. The large-scale structure of the universe, including the hidden web, is an emergent property, arising from the collective behavior of countless particles and interactions over billions of years. While the fundamental laws governing individual particles are well understood, the behavior of the system as a whole exhibits patterns and structures that are not immediately obvious from the laws themselves. Understanding how these emergent structures form and evolve requires both reductionist approaches, which seek to explain phenomena in terms of fundamental laws, and holistic approaches, which study the system as a whole and identify organizing principles and feedback mechanisms. The hidden web is a manifestation of emergence, a product of the interplay between initial conditions, gravitational dynamics, and the complex physics of baryonic matter. The hidden web also relates to the concept of information and entropy in cosmology. The universe began in a state of very low entropy, with matter and energy distributed nearly uniformly, and has been evolving toward higher entropy ever since. Structure formation, paradoxically, involves the creation of local regions of low entropy, such as galaxies and stars, even as the overall entropy of the universe increases. This is possible because gravitational systems have negative heat capacity, meaning they become hotter as they lose energy, and because the formation of structure involves the conversion of gravitational potential energy into kinetic energy and radiation, increasing the overall disorder. The hidden web, as a structured system, represents a local decrease in entropy, embedded within the larger context of increasing cosmic entropy. Understanding the thermodynamics of structure formation is an active area of research, with connections to statistical mechanics, information theory, and the arrow of time. The discovery of the hidden web also prompts consideration of the limits of scientific inquiry. There are fundamental limits to what can be known about the universe, imposed by the laws of physics. The finite speed of light and the finite age of the universe limit the region of spacetime that is observable. The quantum nature of matter and radiation imposes limits on the precision with which certain quantities can be measured simultaneously. The expansion of the universe and the horizon it creates limit the information that can be transmitted across cosmic distances. These limits are not the result of technological inadequacy, but are intrinsic to the structure of the universe. The hidden web, by pushing the boundaries of the observable, brings us closer to these fundamental limits, and future discoveries may reveal phenomena that are at the very edge of what is knowable. The hidden web also has resonance with themes in literature and philosophy, where the idea of hidden or parallel worlds has long captured the imagination. While the hidden web is not a parallel universe in the sense of existing in a separate dimension or obeying different laws, it does represent a layer of reality that was previously unseen, a realm that existed all along but was revealed only through new means of observation. This theme of discovery and revelation, of peeling back layers to uncover deeper truths, is central to both science and the humanities, reflecting a shared human drive to understand and explore. The discovery of the hidden web also highlights the importance of preserving and sharing scientific data. Webb's observations are archived and made publicly available, allowing researchers around the world to access the data and conduct independent analyses. This open-access model accelerates scientific progress by enabling a larger community to contribute to the interpretation of observations and to test alternative hypotheses. The data from Webb will continue to yield discoveries for years to come, as new techniques are developed and as the data are combined with observations from other instruments. The hidden web is just the beginning of what Webb will reveal, and the full scientific return from the mission will unfold over the coming decade. The discovery also connects to the concept of cosmic time, the deep time scales over which the universe evolves. Cosmic time is measured not in human lifetimes or historical epochs, but in billions of years, and the processes that shape the universe operate over these vast timescales. The hidden web formed over hundreds of millions of years, a blink of an eye in cosmic terms, but an eternity by human standards. Understanding the universe requires adopting this cosmic perspective, recognizing that the structures we observe today are snapshots in a long and ongoing process of evolution. The hidden web, as a snapshot from the universe's infancy, provides a glimpse of a time when the cosmos was radically different from the universe we inhabit today, and it offers insights into the trajectory of cosmic evolution. The hidden web also raises questions about the role of chance and necessity in the universe. The initial density fluctuations that seeded structure formation were quantum fluctuations, inherently random, yet the subsequent evolution of structure is deterministic, governed by the laws of physics. The hidden web is thus a product of both chance and necessity, its detailed structure shaped by random initial conditions, but its general properties determined by universal physical laws. This interplay between randomness and determinism is a fundamental feature of the universe, and understanding it is central to cosmology. The discovery of the hidden web also has implications for the search for extraterrestrial intelligence. The presence of a large population of galaxies at early times increases the potential for life to have emerged elsewhere in the universe, though the harsh conditions in the early universe may have made the emergence of life less likely. The search for extraterrestrial intelligence involves not only detecting signals from other civilizations, but also understanding the conditions under which life and intelligence arise and the likelihood that advanced civilizations develop and persist. The hidden web, by providing data on the environments of early galaxies, contributes to this broader effort to understand the prevalence and nature of life in the universe. The hidden web also serves as a case study in the power of collaborative infrastructure. Webb is not just a telescope, but a complex system involving ground-based tracking stations, data processing centers, mission operations teams, and a global network of scientists and institutions. The successful operation of this system requires coordination, communication, and shared standards, and it demonstrates the feasibility of large-scale international scientific collaborations. The lessons learned from Webb will inform future projects, including the design of next-generation observatories and the organization of the scientific teams that will use them. The discovery of the hidden web also underscores the value of patience in science. The observations that revealed the web required long exposures, sometimes lasting many hours, to collect sufficient light from faint galaxies. The analysis of the data required months of work, developing and refining techniques to extract meaningful signals from noisy data. The interpretation of the results required comparison to theoretical models and careful consideration of alternative explanations. This process cannot be rushed, and the discovery of the hidden web is a testament to the value of taking the time necessary to do the work carefully and thoroughly. The hidden web also connects to the concept of the anthropic principle, the idea that the properties of the universe must be compatible with the existence of observers. The universe's parameters, the strength of the fundamental forces, the masses of particles, the amplitude of density fluctuations, are such that structure can form, stars can ignite, and complex chemistry can develop, ultimately enabling the emergence of life and intelligence. If these parameters were significantly different, the universe might be devoid of structure or too short-lived for complexity to arise. The hidden web, as a manifestation of structure formation, is part of the chain of process that made the existence of observers possible, and its study contributes to our understanding of the conditions necessary for life. The discovery also highlights the importance of asking the right questions. The hidden web was discovered not by accident, but through deliberate efforts to observe the high redshift universe and to search for structure at early times. These efforts were motivated by theoretical predictions and by the desire to test cosmological models, demonstrating the value of curiosity-driven research and the importance of pursuing questions even when the answers are uncertain. The hidden web also relates to the concept of simplicity and complexity in the universe. The fundamental laws of physics are remarkably simple, expressible in concise mathematical equations, yet they give rise to extraordinary complexity, from the structure of atoms to the large-scale web of galaxies. Understanding how simplicity generates complexity, and how complexity can be described and predicted using simple principles, is one of the central challenges of science. The hidden web is an example of this emergent complexity, arising from simple initial conditions and simple physical laws operating over cosmic time. The discovery of the hidden web also prompts consideration of the role of aesthetics in science. The images returned by Webb are not only scientifically valuable but also visually stunning, with their rich colors and intricate structures evoking a sense of beauty and wonder. While beauty is not a criterion for scientific validity, there is a long history of scientists being guided by aesthetic considerations, seeking theories that are elegant and observations that reveal harmony and order. The hidden web, with its filamentary structure and interconnected nodes, embodies a kind of cosmic architecture that appeals to both scientific and aesthetic sensibilities. The hidden web also serves as a reminder of the fragility and rarity of the human perspective. Humans have existed for only a tiny fraction of cosmic history, and the period during which we have had the technology to observe the distant universe is even shorter. The opportunity to study the hidden web is a product of our particular moment in history, and future civilizations, whether human or otherwise, will have different observational opportunities and challenges. In the far future, as the universe continues to expand and distant galaxies fade from view, the hidden web may become literally unobservable, hidden not by technological limits but by the fundamental structure of space-time. This underscores the importance of making observations now, while the window is open, and of preserving and sharing the knowledge we gain. The discovery of the hidden web also has implications for the philosophy of cosmology, the study of the conceptual foundations and methodological principles of cosmology as a science. Cosmology is unique in that it studies a system, the universe, of which we are a part and which we cannot observe from outside. This raises questions about the objectivity of cosmological knowledge, the testability of cosmological theories, and the interpretation of observations. The hidden web, as a newly observed feature of the universe, adds to the body of empirical data that grounds cosmology as an empirical science. But it also raises questions about the extent to which our observations are representative of the universe as a whole, and the degree to which our theories are constrained by the data. The hidden web also connects to the concept of the multiverse, the idea that our universe may be one of many, each with different properties and laws of physics. While the multiverse remains speculative and is not directly testable, it is motivated by certain theoretical frameworks, such as eternal inflation and string theory, which suggest that the parameters of the universe may vary across different regions or different universes. The hidden web, by revealing the structure of our universe at early times, provides data that can constrain models of the multiverse and inform debates about the uniqueness and typicality of our cosmic home. The discovery also highlights the importance of interdisciplinary thinking. The study of the hidden web draws on insights from astronomy, physics, mathematics, computer science, and engineering, and it benefits from perspectives that transcend traditional disciplinary boundaries. The most challenging scientific questions often require integration of knowledge from multiple fields, and the discovery of the hidden web exemplifies the power of interdisciplinary collaboration. The hidden web also serves as a focal point for public engagement with science. The images and story of the hidden web have captured widespread attention, appearing in news outlets, social media, and popular science publications. This public interest provides opportunities to communicate the goals and methods of scientific research, to highlight the achievements of space missions, and to inspire the next generation of scientists and engineers. Public support for science is essential for sustaining long-term research programs, and discoveries like the hidden web help build that support by demonstrating the value and excitement of scientific exploration. The discovery of the hidden web also underscores the importance of diversity and inclusion in science. The teams that built and operate Webb, and that analyze its data, include individuals from diverse backgrounds, nationalities, genders, and perspectives. This diversity strengthens the scientific enterprise by bringing a wider range of ideas, approaches, and experiences to bear on complex problems. Efforts to increase diversity and inclusion in science are not only a matter of equity, but also a strategy for enhancing the quality and creativity of scientific research. The hidden web also relates to the concept of legacy in science. The discoveries made by Webb will be studied and built upon by future generations, forming part of the cumulative body of scientific knowledge. The data from Webb will be archived and preserved, serving as a resource for researchers who have not yet begun their careers and for questions that have not yet been formulated. The legacy of Webb is not only the discoveries it makes, but also the tools, techniques, and insights it provides to the broader scientific community. The discovery also connects to the concept of wonder, the emotional and intellectual response to the unknown and the extraordinary. Wonder has been a driving force in scientific exploration throughout history, motivating individuals to seek understanding and to push the boundaries of knowledge. The hidden web, with its revelation of vast structures at the edge of the observable universe, evokes wonder and reminds us of the vastness and complexity of the cosmos. Cultivating a sense of wonder and communicating it to others is an important part of the scientific endeavor, fostering curiosity and a desire to learn. The hidden web also prompts reflection on the nature of progress in science. Progress is often non-linear, with periods of rapid advance interspersed with periods of consolidation and refinement. The discovery of the hidden web represents a moment of rapid advance, opening new areas of inquiry and prompting revisions to existing models, but it also creates new challenges and questions that will require years of work to address. Understanding the trajectory of scientific progress and recognizing that discoveries often raise as many questions as they answer is important for maintaining realistic expectations and for sustaining long-term commitment to research. The discovery of the hidden web also has implications for the concept of truth in science. Scientific knowledge is not absolute or final, but is provisional, subject to revision in light of new evidence. The hidden web was not part of scientific knowledge until it was observed, and future observations may reveal additional structures or phenomena that require further revisions to our understanding. This does not mean that scientific knowledge is arbitrary or unreliable, but rather that it is a process of successive approximation, with each new observation and theory bringing us closer to an accurate description of reality. The hidden web is part of this ongoing process, a step forward in the long journey toward a comprehensive understanding of the universe. The hidden web also serves as a reminder of the importance of skepticism and critical thinking in science. The initial observations suggesting the presence of the hidden web were met with careful scrutiny, with alternative explanations considered and tested. Only after rigorous analysis and confirmation through independent observations did the discovery gain acceptance within the scientific community. This process of skepticism and verification is essential for ensuring the reliability of scientific knowledge and for distinguishing genuine discoveries from artifacts or errors. The hidden web also connects to the concept of scale in the universe. The universe spans an enormous range of scales, from the quantum realm of subatomic particles to the cosmic scales of galaxies and the large-scale structure. Understanding phenomena at one scale often requires knowledge of processes at other scales, and the hidden web exemplifies this interconnectedness. The formation of galaxies depends on the behavior of dark matter particles, the cooling of gas through atomic processes, the nuclear reactions in stars, and the dynamics of gravitational collapse, all of which operate at different scales but contribute to the same emergent structure. The discovery of the hidden web also raises questions about the role of art and visualization in science. The images produced by Webb are not raw data, but are processed and enhanced to reveal features and to communicate information effectively. Choices about color mapping, contrast, and resolution affect how the images are perceived and interpreted. While these choices are guided by scientific considerations, they also involve aesthetic judgments, and the resulting images serve both scientific and artistic purposes. The role of visualization in science communication is increasingly recognized as important, and the images of the hidden web demonstrate the power of visual media to convey complex scientific concepts to broad audiences. The hidden web also underscores the importance of funding and infrastructure for science. The development of Webb required sustained investment over decades, and the scientific return from the mission justifies that investment. However, funding for science is often uncertain, subject to political and economic pressures, and maintaining support for long-term projects requires demonstrating their value to society and to the advancement of knowledge. The discovery of the hidden web contributes to this effort by showcasing the achievements that are possible when resources are dedicated to ambitious scientific goals. The discovery also connects to the concept of the unity of knowledge, the idea that all areas of human understanding are interconnected and that insights from one domain can inform others. The study of the hidden web draws on mathematics, physics, chemistry, engineering, and computer science, and its implications extend to philosophy, history, and the humanities. This unity of knowledge is a powerful motivator for interdisciplinary research and for fostering dialogue across different fields and perspectives. The hidden web also relates to the concept of resilience and adaptation in science. The development of Webb faced numerous challenges, including technical setbacks, budget overruns, and delays. But the project persisted through these difficulties, adapting and overcoming obstacles. This resilience is characteristic of large-scale scientific endeavors, which require sustained effort and the ability to navigate uncertainty and complexity. The discovery of the hidden web is a testament to the resilience of the teams that built and operate Webb and to the power of persistence in the face of challenges. The discovery of the hidden web also prompts reflection on the relationship between science and society. Science is a human activity, shaped by the values, priorities, and resources of the societies that support it and its products. Knowledge and technology, in turn, shape society. The discovery of the hidden web, by expanding our understanding of the universe, contributes to the cultural and intellectual heritage of humanity, enriching our collective sense of who we are and where we come from. It also demonstrates the benefits of investing in science and technology, not only for the practical applications that may emerge, but for the intrinsic value of knowledge and exploration. The hidden web also serves as a case study in the power of observation to transform understanding. Throughout the history of science, major advances have often been driven by improvements in observational capabilities, from the invention of the telescope to the development of particle accelerators to the deployment of space-based observatories. Each new tool reveals previously hidden aspects of reality and prompts new theories and new questions. The hidden web is the latest example of this pattern, and it suggests that future observational advances will continue to transform our understanding of the cosmos. The discovery also highlights the importance of mentorship and education in science. The teams working on Webb include early career researchers, graduate students, and postdoctoral fellows, who are learning the skills and techniques of observational astronomy and contributing to the analysis of data. These individuals represent the next generation of scientists, and their training and mentorship are essential for sustaining the scientific enterprise. The discovery of the hidden web provides a compelling example of the excitement and rewards of a career in science, and it serves as inspiration for students considering scientific careers. The hidden web also connects to the concept of humility in science. The discovery reveals that despite centuries of observation and decades of space-based telescopy, vast regions of the universe remained unseen, and much remains unknown. This humility, the recognition that our knowledge is incomplete and that the universe is more complex than we can fully comprehend, is essential for maintaining an open mind and for being willing to revise theories in light of new evidence. The hidden web is a reminder that the universe still holds many secrets, and that the journey of discovery is far from over. The hidden web, as it recedes into the deeper analyses yet to come, stands not as a conclusion but as an invitation, a structure revealed by light that has traveled across the entire span of cosmic history, carrying with it the imprint of processes that occurred when the universe was young, formless, and rapidly evolving. It is a testament to human ingenuity, to the capacity of instruments to extend perception beyond the limits of the unaided senses, and to the power of careful, patient, collaborative effort to uncover truths that were, until now, hidden behind the veil of distance and time. The web stretches across the sky, invisible to the eye but present in the data, a pattern woven by gravity, shaped by the distribution of dark matter, illuminated by the first generations of stars, and observed by a telescope floating in the cold silence of space, transmitting information across the void to a world where minds strive to understand the cosmos and their place within it.